Welcome to Math 1300, Nunez Community College. Today we will be looking at section 1.3, which is going to be complex numbers. Complex numbers, well, when we try to take the square root of a number, square root of 4 is 2, square root of 9 is 3, and we've messed with square roots in the past. However, if we try to take the square root of a negative number, it does not exist. So they've come up with a system for imaginary numbers. They say that the term I represents the square root of -1. If we can pull a square root of -1 out of a radical, then the term would be considered I. We also look at if we squared both sides. If I square this, I come up with I squared. And if I square this, I come up with -1. That's the two important things about this section. I is equal to the square root of -1, and I squared is equal to -1. That's the two things that we're going to be using in this particular section. So the first thing they want us to do in example number 1 is they want us to simplify. They want us to simplify, and we're going to be simplifying radicals that we couldn't simplify before. By the way, the term radical and square root is interchangeable. It's the same thing. So we have the square root of -25, which again, before we couldn't do. But now we can separate this into the square root of -1 times the square root of 25. The square root of -1 would be considered I, and the square root of 25 would be considered 5. So when we multiply these two together, we get 5i. We put the 5 before the I all the time, or we put the number before the I. So the square root of -25 is 5i. If we had the square root of -9, that would be 3i. Square root of 9 is 3. Square root of -1 is I. Suppose we have a negative out front. Negative of the square root of -169. Well, we're going to write this as the negative of, then we're going to take a -1 out, so the square root of -1 times the square root of 169. So in essence, we're breaking it into almost 3 different things. This negative out front just means the negative of. The square root of -1 is I, and the square root of 169 is 13. So if we put this together in the correct order, it is -13i. Okay, those so far have been numbers that are called perfect squares, because when we take the square root of it, we get a whole number. What happens if we don't have perfect squares? Suppose I have the square root of -24. Well, the square root of 24 doesn't break down. 4 times 4 is 16. 5 times 5 is 25. This is in between 16 and 25. So I like to take the number in question and I like to break it down into its prime factors. Prime factors meaning the prime numbers that multiply to give me that. 24 could be 2 and 12. 2 because it's a prime factor, so that's why I factored it out. 12 could be 2 and 6, and then 6 could be 2 and 3. When we're dealing with a square root, there's an understood number 2 here. Okay, meaning we need 2 numbers that are the same in order to take it out of the radical. So what I'm looking for is I'm looking for 2 numbers that are the same. I do in fact have 2 2's, so I can take a 2 out of the radical. What I don't have pairs of, I have to leave in. So 2 times 3 is 6, so this would be 2 came out of the radical, the 6 had to stay in. So 24 would be 2 times the square root of 6. So I'm going to break this down into the square root of -1 times the square root of 24. Square root of -1 is I. The square root of 24, we just established is 2 square roots of 6. So therefore, to rewrite this in the correct order, it's 2i square root of 6. But again, when trying to break down something that's not a perfect square, take it, break it into its prime factors, and if it's the square root, that means we need 2 of the same number in order to take that number out of the radical. Okay, suppose I have the square root of the square root of negative 8 over 49. 49. Well, what we're going to do here is we are going to take out the square root of negative 1 to make it positive. So that would be square root of negative 1 times, what do we have here? The square root of 8 over the square root of 49. So I'm literally taking out the square root of negative 1. I'm making 8 a square root, and what's on the bottom in the denominator a square root. And we're going to tackle each individual thing. The square root of negative 1 is going to be I. Then we have the square root of 8, which is not a perfect square. So I'll take the 8 and do the prime factors, 2 and 4, 2 and 2. Since I have 2 2's, it's the square root. I can take a 2 out of the radical. This lonely 2 has to stay in the radical. So square root of 8 would be written as 2 square roots of 2. So we have 2 square roots of 2 over square root of 49 is a perfect square because 7 times 7 equals 49. So this will be 7. So in order to rewrite this in the right format, I have 2i square root of 2 over 7. That's how we would write that. Now, in this section, we're going to do operations with complex numbers. This is known as an imaginary number because it has an I in it. Complex numbers are numbers that have a real part and they have an imaginary part. So if we put the two of them together, we have what's called a complex number. The complex number is going to be looked at as A plus BI, where A is the real part and BI is the imaginary part. So when we have our formulas, you're going to see it written as A plus BI. A plus BI. So on the first thing they want us to do, and by the way, an example of complex numbers could be like 2 plus 3i. That would just be an example. The real part, the imaginary part. So what they're going to want us to do first is they're going to want us to add the complex numbers. So the adding of complex numbers would be a plus bi, which is one complex number, plus, since we already used a and b, we'll use c plus di. Again, a, b, c, and d are just numbers that we're putting in. But if we're adding complex numbers, we can only add things that are alike. So we add the reals with the reals and the imaginaries with the imaginaries. So our formula here will be a plus c, the real plus the real, plus the imaginary bi plus di. And the resultant will be our addition of complex numbers. So if they ask us to simplify 3 plus 4i plus 2 plus 7i, we're going to do exactly what it says. Plug it into the formula. It's going to be 3 plus 2 plus 4i plus 7i, which 3 plus 2 is going to give me 5, plus 4 plus 7 is 11i. So 5 plus 11i would be our answer for the addition of the complex numbers? Well, just like addition, we also have subtraction. And the subtraction of complex numbers has a formula just like the addition. So if we have a plus bi minus c plus di, we are going to, instead of add, we're going to subtract the reals and we're going to subtract the imaginaries. So that will be equal to a minus c, but notice it says plus bi minus di. Because the subtraction means we're subtracting the reals and we're subtracting the imaginaries. The plus is just a placeholder separating the two. Okay? So if they give me, in this case, negative 5 plus 8i minus 2 minus 12i, we're going to put it into the formula exactly like it is. The real minus the real, negative 5 minus 2 plus the imaginary minus the imaginary, which is 8i minus negative 12i. And minus a negative is plus. So therefore, negative 5 minus 2 is negative 7. And then we got what? 8i plus 12i, which is going to be 20i. And that is adding and subtracting imaginary numbers. Another thing that we're going to have to do is we're going to have to multiply the imaginary numbers. We're going to have to multiply. And in multiplying, this here is the biggie. Because whenever we have an I squared, we need to turn it to negative 1. Whenever we come across an I squared, we got to turn it to negative 1. And it starts out just like we would in regular old algebra. We got negative 2 times 3 minus 9i. 3 minus 9i. And in here we have what? A monomial times a binomial, so we're going to distribute. So in distributing, that gives me negative 6 plus 18i. The real part comes first, the imaginary part comes second. There's nothing left to do, so that's it. That is the complex number by multiplying. Now, do they get a little harder? Yes, we can do a binomial times a binomial. For instance, 3 plus 4i times 2 plus 7i. In this case, we're going to FOIL because we have two binomials, otherwise known as, well, FOIL is what's otherwise known as. We're actually going to double distribute. Distribute the first one by it and the second one by it. And FOIL is the acronym we use for that. So in FOIL, first times first, 6. Outside times outside, plus 21i. Inside times inside, plus 8i. And last times last, plus 28. But I times I is I squared. So in the next step, we need to combine our like terms here, but we need to turn this I squared into a negative 1, which is going to make this, instead of 28, it's going to make it negative 28. So I'm going to have 6 plus 29i plus 28 times negative 1, which is going to be minus 28. And then when we take negative 28 and 6, I got what? Negative 22 plus 29i. That will be our complex product. Suppose we have something that looks a little bit different, but we can always handle it. And we usually handle it by bringing it back to a plus bi. Suppose I have negative 2 plus the square root of negative 16, that's 16, times 4 minus the square root of negative 9. We're going to take this and try to rewrite this in terms of I. So this will give me -2 plus square root of -16 is 4i times 4 minus the square root of -9 is 3i. So we wrote both of these in terms of a plus bi. Now we're going to do exactly like we did the last problem. We're going to FOIL it together. That's going to give me -8 plus 6i plus 16i minus 12i squared. Which now we're going to combine like terms, and we're going to add 12 because I squared is -1. So that gives me what? 4 plus 22i. 4 plus 22i. And that's about as funny as they get, or as complicated as they get. It really is not that big of a deal once you do several types of problems. Okay, what happens if we have to divide? What happens if we have to divide? Most of the time there's no dividing really going on. Suppose I have 7 over 4 plus 2i. I have a problem here. My problem is that I is in the bottom of a fraction. We cannot have a complex number or an imaginary number in the denominator of a fraction. So in order to get rid of the imaginary number in the denominator, we're going to multiply by something called a complex conjugate. Complex conjugate undoes itself. It undoes the I. So if I have a plus bi, which in this case that would represent a and b, the complex conjugate would be to multiply by the same thing, but with a different sign. Multiply by a minus bi. A minus bi. And you're going to get an answer, but let's show what we're going to do in order to get it. It would be what? Multiplying together, FOIL. So I'd have what? First times first, a squared, outside times outside, minus abi. Inside times inside, plus abi. And then last times last, which would be negative bi squared. Well, if I look at this, my terms with i's in it go away. I got a negative and a positive, and they would go away, leaving me with a squared. And then this is what? Negative b times I squared, which is -1, which would be what? Plus b squared. This is what you get as a result of that. A squared, the first term squared, plus b squared, the second term squared. That would be a complex conjugate. That's the way we're going to get rid of the imaginary number in the denominator. So I'm going to erase this so I have enough room. And I'm going to do what? I'm going to multiply by the complex conjugate. But before I do, I'm going to tell you, I have to multiply by the complex conjugate over itself. Why? Because I don't want to change the problem. And the only way not to change the problem is to multiply by 1. 1 is the only thing that won't change the problem. And this complex conjugate over itself is just a sneaky form of 1. So I'm going to multiply by 4 minus 2i and 4 minus 2i. Again, you can see that this is nothing more than multiplying by 1. So on the top, I now have 7 times this, so I have to distribute, giving me 28 minus 14i on the top. And on the bottom, I said what? It's a squared plus b squared. A is 4, so 4 squared, plus b is 2, so 2 squared. That's 16 plus 4, or 20. So therefore, on the bottom, we'd have 20. That would be our answer. So suppose I had, let's start out with ones that maybe you'll see on your Cengage. Suppose I have 5 over I. Not much to do with it, And you say, well, how can that be a complex conjugate from that? Well, this is just a conjugate of the imaginary number. So in this case, I would multiply by negative I over negative I, the opposite of what you see. And this would give me negative 5I over negative I squared. Negative I squared is 1, so the answer would be negative 5I. And the last one that we have here, 3 plus I over 1 minus I. In this case here, we're going to multiply by 1 plus I, 1 plus I. On the top, we're going to have to FOIL, which is going to give me what? 3 outside, so plus 3I. Inside, so plus I. And then last, which is plus I squared. And that's going to be over 1 squared plus 1 squared, which is going to be what? 2. So here what? This is going to be negative 1. 3 minus 1 is going to give me 2. 3I plus I is going to be plus what? 4I over 2. Now with this one here, if they want us to simplify it farther, I would say all of these have what? A 2 in it. I can factor a 2 out of the top. And if I do, that leaves me with 1. 1 plus 2I. I factored a 2 out of this term and that term. And that's all over 2. I could then cancel the 2's, leaving me with 1 plus 2I. They may or may not want you to simplify down to that. If they do, always look to see what can I factor out of both terms. If I can factor something out that's going to cancel with the bottom, then I do it. And finally, the last example is talking about simplifying powers of I. Simplifying powers of I. Well, powers of I would look like this. I want to write them in terms of I squared. I want to write them in terms of I squared. So if I have I to the 8th power, for instance, and they're saying simplify powers of I. I want to write them in as many I squareds as possible. So this is going to be I squared to the power of 4, because 2 times 4 gives me 8. So I'm writing it as I squared because I squared is equal to negative 1. So I then would come over and say that I squared was negative 1. This is negative 1 to the 4th power. Negative 1 to the 4th power means there's 4 of them multiplied together. Negative 1 times negative 1, so on and so on. That gives me 1 as my answer. Gives me 1 as my answer. This is one of the scenarios that you can have. 1 would be the answer. Another scenario you can have is, suppose I have I to the 9th power. I to the 9th power. Well, I can't exactly like I did here. 8 divided by 4 was 2. Okay, 8 divided by 2 was 4, so I could put it that way. I can't divide 9 by 2. So what I have to do here is write this as I to the 8th times I. Because I to the 8th times I gives me I to the 9th. Then I can take the I to the 8th and write it as I squared to the 4th times I. And then I squared to the 4th is equal to 1 times I. The answer is I. So one of the answers you could get possibly is 1. Another answer you could possibly get is I. You're going to see that there's only 4 answers you could possibly get. Suppose I went I to the 10th. Suppose I went I to the 10th. I would write this as I squared to the 5th. 2 times 5 is 10. Therefore, that would give me negative 1 to the 5th power, which means negative 1 times negative 1, 5 of them. That would give me a total of negative 1 for my answer. So one answer I could get would be 1, one answer I could get would be negative 1, and another answer I could get would be I. What is the only other thing I could get? From looking at it, you'll probably guess it's going to be negative I. So let's look at this one. I to the 11th. Again, Our objective is always the same. Take it and write it as many I squareds as possible. So this is going to be I to the 10th times I, since it's an odd number. I to the 10th could be I squared to the 5th times I. And therefore, this would be what? Negative 1 to the 5th times I, which is going to be negative 1 times I, which is negative I. This concludes section 1.3. We'll see you at the next one.